Okay, lesson 6.7 is where we're at right now. Put the iPads up. We're in notes. We are talking about inverse relations and functions. Some of this is definitely review. So it's just a matter of remembering the idea of what makes a function and also what makes an inverse. So, as we're going to talk about inverses first, a relation that pairs an element A of its domain to an element B of its range has an inverse relation that pairs B with A. Now, that's the fancy definition. What's the shortened form? It flip-flops the domains and ranges. Okay? So if we're talking, but flip-flops speaks to you, doesn't it? That makes so much more sense to you. I mean, officially, when I define an inverse, like a mathematical definition, a relation that pairs A, domain A, with B range, the inverse pairs B with A. Well, what's that saying? That you take A and B and you flip-flop them, okay? You switch them. And so that's the idea of an inverse. So like, for example, here, if we look at this relation, where my ordered pairs are 1.2, 1, 2, 4, and 0, -8. What does the inverse look like? Well, instead of 1.2, 1, it's what? 1, 1.2. Instead of 2, 4, it's 4, 2. Instead of 0, -8, -8, 0. So that's how we get our inverse, is you're just taking your x values and your y values and you are flipping them. Okay? Over here to the right, the notation for an inverse, for just a function, we say f of x. For inverse notation, we're going to say f to the negative, we read it f inverse, but it looks like f to the -1 power is what it looks like. And so that's what you'll see us using when we write inverses. Okay? So, let's look at example 1 here. And this is very basic. Don't make it any more difficult than what it is. We're going to start with asking the question of what is the inverse? So if the given function or relation is 0, -1, 2, 0, 3, 2, and 4, 3, what is the inverse? Instead of 0, -1, what does it become? -1, 0. Instead of 2, 0, 0, 2. Instead of 3, 2, 2, 3. Instead of 4, 3, 3, 4. Easy enough? Okay, I'm going to keep reminding you to find the inverse. You flip x and y. If we're going to do something else with B, we'll come back, or with A, we'll come back to it here in a moment. Let's talk about B. Let's also practice with our inverse here. Okay. What are you thinking for the inverse? Instead of 0, -5, it's -5, 0. -4, 1. -3, 2. -3, 2. Okay, so inverse. You flip x and y. You switch them. Now, there's a part C here, and it says to state whether the inverse of the above tables are functions. So, do you remember how to tell if something is a function? Okay. If we were looking at a graph, we could talk about the vertical line test. And we'll talk about that a little bit later in the notes. And we could graph this. That's more work than I want to put into it, though. Okay? So you could graph it, and the idea of the vertical line test is if you draw a vertical line, it just touches one point, it passes the vertical line test. If it touches more than one point, it fails the vertical line test. Now, the idea here, the easier thing to do is just look at your x values. If it is a function, each x value pairs with exactly one y value. If it's not a function, we tend to see x values that they'll repeat. because they possibly pair with different y values. Now, okay, with that in mind, what about a? And it's just asking about if the inverse is a function. -1, 0, 0, 2, 2, 3, 3, 4. Is that going to qualify as a function? Yes, because each x value pairs with exactly one y value. None of the x's are doubled up with different y's. So I'm going to, off to the side here, write function, as in, yes, it is a function. And I'm going to put a reasoning down in that each x value pairs with exactly one y value. So that's my explanation. If you look back in your notes later, you're trying to figure out, why did you say this was a function? Each x value goes with one and only one y value. Okay. Now let's look at example B. Again, we're asking about, is the inverse a function?
No.
I'm hearing some no's. Why not? Okay. So my x values repeat. Now, what do you notice about this -3? It's there twice, but what does it do both times? It goes to 2. So if the last one was a function because each x value pairs with exactly one y value, does this x value of -3 pair with more than one y value? No, it's the same one. If I were to graph the ordered pair, -3, 2. Left 3, up 2. Make a point, yes? What if I graph the ordered pair, -3, 2 again? A dot on top of a dot. Can you tell a difference? It's still one dot, right? Does that one dot pass the vertical line test? Okay. So this is the catch. Okay. I'll show you the alternative here in a moment. But this is the catch in that this one is still a function. I know that it looks like it shouldn't be because the -3 repeated, but the -3 repeated and the 2 repeated. So sure, you can call this a trick question if you want. But so this one is also a function for the same reason as above, in that each x value pairs with exactly one y value. And if you're questioning the -3, the comment I'm going to write here so you have it is the repeat pairs the same x and y value together. The repeat pairs the same x value and y value together. Okay, so yes, it is a function. Each x value pairs with exactly one y value. The repeat pairs the same x value and y value together. Now, if you're sitting here wondering, how do I know? Let me give you a what-if example here. Okay? What if that last inverse table instead had read -5, 0, -4, 1, -3, 2, -3, 3. So all I did is change one little value there. But what does that say? Is this table of values represent a function? Why not?
Not every x value has
Yeah. Remember earlier we said each x value is paired with exactly one y value. Well, what about the x value of negative 3 here? It's paired with 2 and it's paired with 3. This is an example of a set of ordered pairs that are not a function. So if you're looking for an example to be able to refer back to later, write this down. This is an example that is not a function. And the reason? Because the x value of negative 3 is paired with 2 different y values. The x value of negative 3 is paired with 2 different y values. 2 and 3. What?
This has been easy so far.
And this right here, this is definitely Algebra 1 review at this point. I mean, in fact, to be honest, I feel like a lot of this lesson, maybe not quite all of it, but a lot of this lesson should be familiar at least.
I don't remember the other sections.
So, okay, got what you need there? Okay, before we turn the page, there's a little bit about information about finding the inverse of a function. Up at the top of the screen, up at the top of the page, we found the inverse of just a set of ordered pairs, right? And it was to take your x values and your y values and you reverse them, you flip them. Okay, so now we're going to talk about how do we find an inverse of an equation, okay, when it's in equation form. So a couple of key points here. First of all, it doesn't tell me how to find it, but the graph of f of x and the inverse of f of x will always be reflections of each other in the line y equals x, which is the perfect diagonal line. So if you can visualize it, it's the line that goes through 0, 0, 1, 1, 2, 2, goes up 1 over 1 from 0. That's the perfect diagonal line. And so that line y equals x, a function and its inverse reflect across that line. So it's not your typical reflection of up and down or left and right, but it's kind of this diagonal reflection. Now, talking about how to find our inverse. First of all, in order to find the inverse, we're going to switch the variables x and y. So x's become y's, y's become x's. And then after we switch those variables, our job will be to solve for y. So we're going to switch x and y, and then we're going to solve for y. We're going to talk about how to know if it's a function. We'll talk more about that on the back side. So for an inverse function to be a function, it must pass the typical function test. So like the idea that the x's cannot repeat or the vertical line test, those are the type of things it has to pass. And then point 4, when we get done, once we're done finding the inverse, instead of writing y equals or f of x equals, we're going to use the f inverse notation, which is f, it looks like f to the negative 1 of x. Okay, that's what I'll use for inverse notation. Okay, flip to the back when you're ready, and we'll try an example here. Here we go. Example A, what is the inverse of the relations y equals x squared minus 1? Okay, what was the first thing we had to do to find the inverse? Take x and y and switch them, right? So instead of this saying y equals, it's going to read x equals. Instead of x squared minus 1, we're going to write y squared minus 1. So that is your first step. And if you need a step to remind yourself, the step I did here is I switch to x and y. After we switch x and y, what do I do to get this in a better form? If you go back to the steps on the front, it said we're going to switch x and y, and then we're going to solve for y. Okay? Like any other equation, before we work with it, we want it to be y equals 4. So, if this is x equals y squared minus 1, how do I get y by itself? If it's y squared minus 1, let's start by adding 1. If I add 1 on the right, add 1 on the left. Are you guys confident enough that I can flip my sides as I go here? On this left, I'm going to have x plus 1, correct? On the right, I'm going to have y squared. How do you guys feel if I go ahead and flip it and say y squared equals x plus 1? Can you see what I'm doing there? So it was x plus 1 equals y squared. I'm going to say y squared equals x plus 1. How do I continue solving for y? Okay. If it's y squared, how do I get that squared to go away? We take the square root. If we square root the left, square root the right. What's the square root of y squared? Y. What's the square root of x plus 1? Square root of x plus 1, and what else? Square root of x plus 1 and the negative square root of x plus 1. I say this every time we do this. When you're solving an equation and you take a square root in an equation setting, what do we have to tack on? Plus or minus. Every time you take a square root in an equation setting, you tag on a plus or minus. So this is really y equals plus or minus the square root of x plus 1. Now, we got y equals, right? So the only other way to really finish this off is that instead of y equals, do you remember what it showed as the inverse notation? Just to indicate that this is inverse, we're going to use f inverse of x equals plus or minus the square root of x plus 1. Okay, f inverse of x equals plus or minus the square root of x plus 1. Now, before I move on to B, there's one other piece we need to talk about. And I didn't get a chance to log back into homework this morning and check out the setup again, but I believe they're going to ask you about, are these functions or not? Okay, we talked on the front side, if it's an XY chart, how to tell if it's a function. Well, now the question becomes, how do I tell if this is a function? Okay, and there's two options. One, if you know what the graph is, you can think about the graph, and I can help you a little bit with that on this one. The other thing, try some x values. See what happens when you start plugging some x values in. Okay, so one thought. Go back to the very beginning for a moment. Y equals x squared minus 1 was my original function. Can you visualize the graph of y equals x squared minus 1? Or forget the minus 1. What about y equals x squared? You're supposed to know the graph of y equals x squared. What is that? Y equals x squared is the graph of a what? Parabola. The U shape. Okay. Y equals x squared is that parabola, yes? Now, think about a function and its inverse reflect across the line y equals x. So start trying to visualize. If you have this vertical parabola and you reflect it across the diagonal line, okay? If we reflect it across the x-axis, it's just going to go upside down. If we reflect it across the y-axis, it's still going to be right side up. It's just going to flip over. But what about this diagonal line?
It's still downside. It doesn't change. But it's still reversing, but we don't notice that it's reversing because it's equal.
Not exactly. It's going to turn and it's going to open sideways.
Why would he do something like that?
Okay? And for proof, what I would say is take a piece of paper, draw a vertical parabola, and then fold the paper diagonally and see how that paper ends up. I don't know if I have, I don't think I have a blank piece of, I don't have a good piece of paper for this. Actually, where am I?
What you looking at there, Ezra? She's not wrong.
I'm not wrong. Okay, that's a good thing.
Not wrong.
Interesting how he puts that, but, take or even just take, like, right here. If I put a diagonal crease in my paper, here, will this work? Ooh, this might work. Can you guys see it showing through there?
Not even in the slightest.
Right there is my parabola on the other side of the paper. So here's the vertical parabola, diagonal fold, there it's sideways. Okay? So now, all of that, the whole point of me trying to do that, is if this down here is a sideways parabola, is that a function? No, it's not a function because exactly. It fails the vertical line test, folks. Yes, you know that. And so this inverse is not a function in this case. Now, if you're thinking, oh, that's great and dandy for you, Mrs. Sargent, but I wouldn't get that. Here's one other thought. Pick a random value x. If I put in 3. 3 plus 1 is 4. The square root of 4 is 2. But what's it say right here? Plus or minus 2. So those ordered pairs, we put in 3, but we would get what out? 2 and negative 2. If you get the ordered pairs 3, 2, and 3, negative 2, is that a function? My 3's repeat. My 3's pair with 2 different y values, so it's not a function. And we will continue notes tomorrow. Homework will due the following day, Thursday. You can put it back in the basket. If you need it, you can keep it. Have a good day, guys.
Don't do this tomorrow. And we just sit. I like that idea.